Good evening. I'm Jeffrey Kozak, Director of the Library and Archives at the Marshall Foundation, and I'd like to welcome you to the special event of the Marshall Legacy Series. We can think of no better person than Dr. Frank Settle to talk about the race for the atomic bomb. Early in World War II, General Marshall said, "Warfare today is a thing of swift movement, of rapid concentrations. It requires the building up of enormous firepower against successive objectives with breathtaking speed. It is not a game for the unimaginative plotter." This Speed and Fury sequence of the Legacy series explores the technological advances in vehicles and weapons produced during World War II that substantially increased the speed and effectiveness, the speed and power of warfare. Airplanes and tanks were used in World War I, but their effectiveness and their role in military operations were greatly expanded in World War II. The Jeep emerged as the iconic vehicle of the war. In the end, however, the atomic bomb unleashed the fury of a nuclear chain reaction that changed the face of warfare and ended World War II. During World War II, President Roosevelt assigned oversight of the Manhattan Project to General Marshall and Secretary of War Henry Stimson. The race was on to build the first atomic weapons. Dr. Settle will describe Marshall's role in both the Manhattan Project and obtaining Japan's surrender. Frank Settle is a professor emeritus of chemistry at Washington and Lee University and also director of the Alamos Digital Library for Nuclear Issues. He taught chemistry at the Virginia Military Institute from 1964 to 1992. Before going to WNL in 1998, he was a visiting professor at the U.S. Air Force Academy, a consultant at the Los Alamos National Laboratory, and a program officer at the National Science Foundation. At WNL, he developed and taught courses on nuclear history, nuclear power, and weapons of mass destruction for liberal arts majors. His new book, researched at our Marshall Library, General George C. Marshall and the Atomic Bomb, is available for you to buy after his presentation. Please welcome Frank Settle.
Well, thank you. It's good to be back. This talk is going to be more about the technical scientific part, but I've tried to interpret it so you will be able to understand how the bomb was actually developed. In the race for the ultimate weapon, I would say of all World War II weapons, the atomic bomb was the ultimate weapon. And Marshall certainly, as Jeffrey said, had a hand in the development and the use of the atomic bomb. Marshall, as you well know, did not seek the limelight, was not a micromanager. He assigned the Manhattan Project to General Groves, and he supported General Groves. He went to Congress and got the money for the Manhattan Project. And he was trusted enough by Congress that he could say, "Trust me, this is an important project." What I want to do this afternoon is take you through this. This is the presentation. I want to give you a little background in nuclear physics, because if you don't understand a little bit about nuclear physics, you're coming to the technical part of the atomic bomb. Doesn't make a whole lot of sense. Then I want to talk a little bit about atomic bomb possibilities. This is for the United States, for Britain, for Germany. These were the people that were in the race initially for the atomic bomb. Then we'll look at the Manhattan Project and producing the U-235 and the Plutonium-239 that were used in the atomic bombs that were dropped on Japan. And then we'll actually look at the construction of the atomic bombs in 1945. And as many of you know, they were known as Little Boy and Fat Man. So, 1932 was a seminal year in nuclear physics. The neutron was discovered. And with the discovery of the neutron, this led to the discovery of nuclear fission. And the players in this were James Chadwick on the upper left-hand corner, a student of Rutherford, who was one of the patriarchs of nuclear physics. Chadwick discovered the neutron. Otto Hahn and Louis Meitner discovered fission in Germany in 1939. Leo Szilard, the wild Hungarian, had the idea for a nuclear chain reaction. And Glenn Seaborg in California, University of California, Berkeley, discovered plutonium. So uranium-235 and plutonium-239 were the ultimate results of this era in nuclear physics. So let's just take a look for a minute. Chadwick is the discovery of the neutron. Basically what Chadwick did, the neutron was the last nuclear particle to be discovered. The electron had a charge, the proton had a positive charge, but the neutron had no charge. So it was hard to detect a neutron, and it remained hidden. The electron was discovered in the late 1800s, the proton in the early 1900s, and it wasn't until 1932 that the neutron was discovered, mainly because it didn't have a charge. And all the apparatus for looking at nuclear particles depended on the particle having a charge. So basically Chadwick took alpha rays from plutonium, which is the element Madame Curie discovered, bombarded beryllium, another element, and basically produced neutrons. And the way you look at a neutron is you can't see the neutron, but if a neutron hits a charged particle, you can see what it does to the charged particle. So it works on banging into something, a charged particle, and you can see the vapor trail in a cloud chamber here, which was used to detect charged particles. Now, the thing I want to impress with you, there is Chadwick's apparatus. Looks like something for a Cub Scout science. Okay? Amazingly, the discoveries in physics were made with very simple apparatus. Very simple apparatus. Okay? Now, you're going to have to follow me a little bit. There's an element, uranium. And uranium had been discovered way back in the 1700s. People had not done much with it, really. They used it to color glass, but it just wasn't a very interesting element. However, in 1935, the interest in uranium began to pick up, and it was determined that uranium had two isotopes. Now, an isotope, basically, the identity of an element is determined by the number of protons. And notice that these two isotopes have the same number of protons. So they're uranium, right? But they're slightly different. From the nuclear physics point of view, they're greatly different. Uranium-238 has 146 neutrons, and uranium-235 has 143 neutrons. Now, Dempster used something called a mass spectrometer to separate these two isotopes. And he determined that uranium-238 comprised 99.3% of uranium, and the other isotope was only 0.7. Okay, can you remember that? All right. Because that's going to be important. Now, in Berlin, Germany, 1938, a team of Otto Hahn, Fritz Strassmann, and Louis Meitner discovered fission. It's an interesting discovery because the chemists were working again with very primitive apparatus. Looks like, you know, a kitchen or something. Anyway, Hahn and Strassman were working in Berlin. They started out as a team, but Lisa Meitner was Jewish, and she had to go, she fled, really, to Sweden. Meitner's the brain of this operation. Hahn and Strassman are chemists. I'm a chemist. We have great respect for physicists. Okay? So, the way they discovered it was, and don't let this blow you away. All right, basically, they were bombarding uranium, remember uranium, with neutrons, remember neutrons, and they thought they would get radium. Radium was an element that had been discovered by Madame Curie, right?
Yeah.
Right.
Radium's right next to uranium in the periodic chart. I always hate to give a lecture in a room without a periodic chart. Makes me very nervous. Okay? So, what they expected was, if you bombard uranium, you're going to get radium. In the process of the chemistry, and notice this is chemistry, right? They had to add a little barium in order to separate the radium from the rest of the uranium. You with me? When they got to the final step, they couldn't separate what they thought was radium from barium. So what this meant was they expected radium 88 protons, pretty close to uranium at 92, but they got barium 56 protons, which is way far away from uranium, which meant that they had split the atom. Amazing. Now, what was their reaction? Well, it really wasn't there. It was Otto Hahn. Otto Hahn is not one of my favorite people, but we won't go into that. As chemists, we must actually say the new particles do behave like radium, do not behave like radium, but in fact like barium. As nuclear physicists, we cannot make this conclusion, which is in conflict with all experience in nuclear physics. In other words, the nuclear physics people said, you're going to get radium. And they got barium. And they were very humble in the presence of nuclear physics. Okay? Now, Hahn sends his results to Meitner, who's in Sweden. Meitner says, what happens is the neutron hits the uranium nucleus, it makes it a little bigger and it begins to vibrate. And finally, it comes apart. And since both pieces are positively charged, positively charged repel each other, this thing flies apart with a whole lot of energy. And Meitner and Hahn, Meitner and her nephew, Otto Frisch, who came from Germany to visit his aunt in Sweden during Christmas. Anyway, Meitner said the amount of energy that's generated when these things fly apart is equal to mc squared, where m is the difference in mass between what you start with and what you wind up with. In other words, mass was disappearing. This was more massive than the two pieces together. And this confirmed Einstein's E is equal to mc squared. It also said you can get a hell of a lot of energy out of this fission. Now, this is one little bitty atom, so it's not much energy, but if you multiply that by Avogadro's number, which is something times 10 to the 23rd, then you got a lot of energy. You with me?
Yeah.
All right. So now we know that fission occurs. Fission can produce tremendous amounts of energy, much more so than any chemical reaction. Okay. Now the question comes, and we go to Columbia University Enrico Fermi had gotten the Nobel Prize. He's an Italian. He went to Stockholm to get the Nobel Prize, left Italy, and he went directly to the United States. He never went back. Okay. He's working at Columbia, and he says, we need to know which isotope, or maybe both, undergoes fission. Remember the two isotopes. The one, 238, lots, 235, not much. He sends a sample of uranium to Alfred Neer at the University of Minnesota. Neer has a mass spectrometer and can separate these two isotopes. He separates the two isotopes. He puts the samples on a postcard, puts tape over it, mails it back to Fermi. Okay? Fermi then exposes the two samples to neutrons. The neutrons hit the 235, and that's the isotope that undergoes fission. That's bad news, right? Because it's only 0.7% of uranium. We got a problem here. Okay? Now, the next thing, Leo Szilard, the mad Hungarian. There were a bunch of mad Hungarians that came out, scientists, physicists, mathematicians, that came out of Hungary about the same time. And Szilard was probably the craziest of all of us. If you want to read something fun, read his biography. Leo, the story goes that Leo was in London. He had migrated from Hungary to Germany with the Nazis. He saw the Nazis were going to take over Germany. He was Jewish. He went to Britain, and then he left Britain, and he wound up at Columbia University with Fermi. But on the sidewalk in England, when the traffic light changed, Szilard had a vision of a nuclear chain reaction. And the nuclear chain reaction was, remember now, you get barium and krypton for two fission products, but you also get some extra neutrons. And if you have extra neutrons and you have more 235, then you've got a chain reaction. You with me?
Yeah.
Okay? Now, we call these generations. So this would be first generation neutrons, second generation neutrons, fourth. In an atomic bomb, you need 80 generations of neutrons before the thing blows itself apart. So you got to keep that uranium together for 80 generations. Now that's about a microsecond, if you do it right. Okay. Now, in California, the University of California, Berkeley, that's another foreign country, right? The physicists were now using this kind of thing. This is called a cyclotron. Physics had upscaled from that shoebox to this stuff. They were using this cyclotron to bombard the other isotope, 238. And they found out that 238 will convert to 239, which converts to the first man-made element, Neptunium. Neptunium has a pretty short lifetime, and it converts to Plutonium. Okay? So the 238 isotope is not totally useless in the bomb business. You can bombard 238 and you can get plutonium 239, and that is bomb material. These are the guys, Edward McMillan and Glenn Seaborg. Glenn Seaborg went on to get a Nobel Prize in chemistry for this work. They were working with very small amounts of material. This is a microbalance. These are micro pipettes. So this is very tedious work. Take the material out of that big machine and put it on a laboratory bench. Okay. Now, again, don't worry about this. There's a lot of chemistry here. This is just down and dirty chemistry. If you took chemistry 101 and you went in the lab, you'd probably do some of these reactions. Precipitation, oxidation, reduction. It's not rocket science, it's just down and dirty chemistry. But the bottom line is, this was the discovery of the element with atomic number 94. Now, if that was all there were to it, okay, so you discovered a new element. Check it off. But the next slide, they bombarded 239 with neutrons, and it undergoes fission. So now you have another route to atomic bomb. Okay? Now, as I tell my students, this is the key slide. Don't let it blow you away. Basically, neutron cross-section is the ability of that uranium atom to capture a neutron. Okay? That ability to capture a neutron depends on how fast the neutron is going. If it's a slow neutron, the U-235 will capture it and undergo fission. So it looks like slow neutrons are pretty good things for bombs, right? What about the 238? The 238 requires a neutron of about this speed, and it will capture that neutron, become plutonium-239. So you got both uranium isotopes are participating in this. Once you have plutonium-239, it actually undergoes fission better than uranium-235. You with me? There'll be a quiz. All right. Okay, now we've gotten the down and dirty nuclear science out of the way. Now we can have a little fun maybe. So, these are the people that were involved in the what I call alerting governments to the possibility of an atomic bomb. These three guys right here, Leo Szilard, Edward Teller, and Eugene Wigner. They were all Hungarian scientists. They are the ones who went to Einstein and got Einstein to approve a letter to Roosevelt. Here's Otto Frisch, remember him, Lise Meitner's nephew, and Rudolf Paris. They were German immigrants. They fled the Nazi regime. They were in England, and they basically alerted the British government to the possibility of an atomic bomb. And here we have Werner Heisenberg. Werner Heisenberg was the prime scientist in the ill-fated German bomb crash. He's seen there with Niels Bohr. There's a very famous meeting of Heisenberg and Bohr. There's actually a play called Copenhagen, which is written about that meeting. Okay, so let's look just for a minute. The origin of the Manhattan Project. So, Wigner, Teller, and Szilard drove out to Einstein's summer home on Long Island, and basically Szilard said, have you ever thought about the possibility of a chain reaction? And Einstein said, no, never thought about that. And so Szilard explained to him what, and he said, yeah, that really makes sense. And Szilard said, well, you know, we're not that well known, none of us, but you are. and we want you to write a letter to President Roosevelt and alert him to the possibility of an atomic bomb. So basically, they went back, Lord drafted the letter, Einstein signed it. But if you have a letter to the president, you don't drop it in the mailbox. There's the letter, and you can pull it up on the web. Now, what you need is a delivery boy. And the delivery boy was Alexander Sachs. Alexander Sachs was a Lehman Company executive. He had worked in the Roosevelt administration, and he had an inside track to see the president. The letter was signed on August 15th. Sachs did not deliver the letter until October. President Roosevelt was occupied in September 1939 with a little event that happened in Europe. A little distracted. So, Sachs goes in, gives him the letter, and Sachs had an interest in science too, so he kind of explains some things. Roosevelt says, Alex, are you telling me the Germans might blow us up? And Sachs said, yes. He said, this demands action. And he immediately appointed a committee chaired by Lyman Briggs, who was the director of the National Bureau of Standards, to investigate the possibility of an atomic bomb. Now, on the other side of the Atlantic, Otto Frisch and Rudolf Peierls drafted what I consider one of the finest pieces of scientific communication that's ever been written. This is called the Frisch-Peierls Memorandum. It is a two-part memorandum. One is for the politicians, the government people. The other is for the scientists. And it is a well-written, well-drafted document. And since Britain was in the war, was well engaged in the war, a committee was formed to study the possibilities of an atomic bomb. So the committee was established in 40, and the final report was done in April. The final report was done a little over a year later. And they assembled scientists at universities and also at ICI, which is the DuPont of Great Britain, the big chemical company. So the interesting part of this, the Bond report was very useful to the U.S. as they began to develop their program. So this contributed to the Manhattan Project. The Brits shared that with us. Now, Lyman Briggs committee didn't really do a whole lot. They sat around and, contemplated what might happen. This guy right here, Vannevar Bush, said, you guys aren't moving fast enough. This is an important project. I need to get this in front of the president. I need to get some information in front of the president so we can take some action. Now, Bush was the chairman of the Carnegie Foundation. He was an electrical engineer from MIT. He had been in administration at MIT. So he had some clout. And he met with President Roosevelt, and he brought the evidence from the Bond Committee, and he brought some evidence that had been established about the possibility of the bomb. And Roosevelt appointed a top policy group. This was in October 1941. Now notice what the Einstein's letter was August 1939. We got 2 years lapse in this while we were kind of dithering around. So you got Vice President Wallace, Secretary of War, which was basically Secretary of the Army. And here's where Marshall comes in. Roosevelt appointed Marshall. He thought the Army would be better suited to manage this project than the Navy. He had kind of fallen out with the Navy at that point anyway. You got Bush, and you have James Colett, a chemist who was president of Harvard University. So you got Harvard and MIT represented. Now, the Manhattan Project itself. President Roosevelt, Stimson, and Marshall worked together on the project, as well as many, many other aspects of World War II. Then you have the lead scientist, Robert Oppenheimer, and the real driver of this thing, General Leslie Groves. Okay? And then, of course, you have President Truman, who really found out about the bomb after Roosevelt's death. He really didn't know anything about the atomic bomb. Now, here's what Bush took to Roosevelt in 1942. Here we have the scientific side, and here we have the industrial side. Bush recognized that this was much more than some laboratory science project. It was going to be a huge industrial operation. So you notice that you've got Murphy, who was chairman of Standard Oil, you got Union Carbide, you got Kellogg, you got Westinghouse, you got a lot of the big players involved in this. Over here you have the scientists, many of whom were Nobel Prize winners. And here's how they decided to sort of divide up the work. Measurements, we'll talk more about how you separate the two isotopes. These had to do with how you separate the two isotopes. So Bush presents this to President Roosevelt. And shortly thereafter, they begin to let contracts to various universities and chemical companies, etc. The one that I would point out to you is the University of Virginia had a contract in this book. But you'll notice most of these many were universities. There were some capital standard. This is the beginning of the military-industrial complex, if you will. Now, shortly after Roosevelt received that information, he said, I'm greatly interested in your report. I think the whole thing should be pushed, not only in regard to development, but due regard to time. Time's very much of the essence. I have no objection to your turning out future progress over to the War Department on the condition that you yourself are certain that the War Department has made adequate provision for secrecy. And Marshall was obsessed with secrecy. Okay? Now, a little later, this is in March, in June, Bush wanted to go full tilt. He said, we're ready to start, breaking ground on these projects. And Roosevelt says, okay, I think you best keep this in your safe. Okay? Now, the Army takes control. General Wilhelm Steyr, a West Point graduate, was appointed by Marshall as the liaison to Bush's scientists. This was actually before the Manhattan Project was officially turned over to the Army. So Steyr's the liaison. The first manager of the Manhattan Project was Colonel James Marshall. Colonel James Marshall, another West Point graduate, an engineer, was called to head up the initial Army effort on the Manhattan Project. Breon Somerville was the chief of Army Supply Services. In other words, he was going to control all the material that you needed to build it and give it priority. And last but not least was Leslie Groves. Groves didn't want the job, and basically Bush's initial choice was Somerville to hit the Manhattan Project. Marshall said, no way. We're invading North Africa. I can't give you my chief of supply services. You can't have it. So I said, okay, how about Steyr? He said, in Somerville said, no way. He's my chief operating officer. And Marshall said, well, find somebody. Give me Steyr or find somebody. So Somerville goes to Groves, asks Groves, told Groves that he had a really important assignment to win the war. Groves said, you know, I've been in Washington for too damn long. I built the Pentagon, and I want a combat assignment. And the response was, do this, you can win the war. So Groves reluctantly took the assignment. And luckily, and Marshall immediately approved it. So luckily for everybody, Groves got the assignment. Now he was a son of a bitch as far as a driver. He was not interested in winning friends and influence and people in order to get the job done. And so he was abrasive, but he got, basically he's responsible for the success of the Manhattan Project. Okay, now we got to go back to the science. So you got this natural uranium. You've got to get a high concentration of 235. You got to have uranium that has 90% 235. Remember, from a chemistry point of view, uranium-235 and uranium-238 are exactly the same. So I can't use chemistry to separate those two. I got to use physics. Make sense? They have the same number of electrons, same number of protons. If I try chemistry, no separation. But I can use physical methods, and we'll look at that in a minute. The other route, remember that 238 absorbs neutrons and becomes plutonium-239. So there are two ways to get there. There are two types of reactors. The Germans chose to use a graphite reactor. That was one reason for their failure. Not that graphite reactors don't work, but they used impure graphite. That was part of their problem. We chose to use the uranium heavy water reactor. Okay, so let's look at how you get bomb material. You start out by mining uranium. Now this is like any other metal, iron, copper, whatever. You go through the same process. This is metallurgy 101. Okay? You wind up with uranium oxide, basically. You grind it, you crush it, you do all this stuff. Okay. Now, I said that you couldn't separate 238 from 235 by chemical means, right? But you do have to do some chemistry because you can't throw uranium oxide into one of these processes. It turns out that you really have to convert uranium to fluoride compounds. One is uranium tetrafluoride and the other is uranium hexafluoride. Hexafluoride is, let's just say it's a gas. There's a chemist in here, somebody knows what's going on. We're going to call me on it. At room temperature, it's a liquid, but it doesn't take much to make it a gas. Okay? So this is used in gas diffusion and centrifugation. Uranium tetrafluoride is used in the electromagnetic separation. It turns out that in the race for the bomb, all methods were used. We used every method possible. And we'll see this in a minute. So, the centrifuge method, basically, you put all these atoms in the centrifuge and you spin it. And guess what? The heavy stuff goes to the outside and the light stuff stays on the inside. So the uranium hexafluoride 238 goes to the outside and the other, so you can kind of use a centrifuge. That's what the Iranians are doing. That's basically their process. Okay? The other is gaseous diffusion. And here you set up a racetrack. And if you've got a heavy runner and a light runner, they're pretty close together, right? But if you run them long enough, the light stuff will come out ahead and the heavy stuff will stay outside, and the light stuff goes to the inside. Now, the electromagnetic separation using uranium tetrafluoride, you run it through a magnetic field, charge it up, run it through a magnetic field. The light stuff is less affected by the magnetic field than the heavier stuff. Okay? So there are the separation methods. Now, Jesse Beams at the University of Virginia did a lot of centrifuge research. Unfortunately, the centrifuge process was not robust enough. Uranium hexafluoride is a very corrosive material, and they didn't have the material to build the centrifuges. And so that process, while it was investigated at UVA, did not wind up as being used in the Manhattan project. Now, the gaseous diffusion plant, basically you set up, this is kind of like a runner with barriers, you know, what do they call it, hurdles, like this. So you have hurdles. The hurdles in this thing were porous barriers, okay, and they help separate the two isotopes. Now, you can't just, as I said, the two runners, the two isotopes, are very close in weight. So you're going to have a lot of barriers in order to get them separated, right? And this is Oak Ridge, Tennessee. This is the gaseous diffusion plant, the largest industrial building under one roof ever built up to its time in the U.S. It was about half a mile long and 6 stories high. And it was loaded with these, each one of these represents one of those hurdles. So you run this stuff through a lot of hurdles. The electromagnetic separation was done in what was called the Y12 plant. And you had a whole lot of these, what they really were mass spectrometers. Each one of those is separating the 235 from the 238. This is the inside of Y12. A lot of, particularly women from East Tennessee, young women from East Tennessee were employed in the Y12 plant. And basically they sat there and kept the magnetic field straight where it ought to be in order to get to separation. 9,000 women in this place. And this is a real view of Y12. Okay. Thermal diffusion was not that important, but they basically used it at Oak Ridge because they already had the power plant. They just used the heat from the power plant for thermal diffusion. Now, you start out with U-235 at 0.7%. You use thermal diffusion to get it up to 0.86%. You run it through gaseous diffusion, you get it up to 7%. You run it through the electromagnetic separation one time, 15%, 2 times, 90%. And that's how you made the U-235. This was all done at Oak Ridge, Tennessee. All right, going back to the other method, so using a nuclear reactor to produce plutonium. This first reactor was built under the football stadium at the University of Chicago. And it was called CP1. And Enrico Fermi and Leo Szilard were the guys that built the reactor. It was basically a pile of graphite. There's the reactor right there. The pile of graphite bricks with a lot of uranium stuck in with. I said that the U.S. didn't really use graphite. Kind of a mistake. We did use graphite. We used pure graphite, not impure graphite. So the first chain reaction, controlled chain reaction, was run on December the 2nd, 1942 at the University of Chicago. Okay? Another reactor was built at Oak Ridge, Tennessee. It was kind of a pilot plant, the next step up, if you will. But the reactors which produced plutonium for the atomic bomb were at Hanford, Washington. Now, I don't know how many of you have been to Western Washington, but Western Washington is a desert, basically. But it's on the Columbia River, and they needed water to cool these reactors. Okay? Again, a massive construction project, 35,000 workers to get this thing going. And we need pipe fitters, we need carpenters, we need work. Labor actually became a problem because there weren't enough people, enough skilled people to do this. Okay, now, there's the B reactor at Hanford. You can see considerable, you can see from the size of the people, pretty big operation. It turned out that the folks at the University of Chicago, the physicists at Chicago, had designed a reactor. And the engineers from DuPont, who actually had built this thing, said, you know, we ought to add a little bit for safety, or just in case things don't work. And this poem sort of sums that up. We call up a type design hewn strictly by the long-hairs son. Those were the guys, that physicists at Chicago. To us, it looked almighty fine, the honey we'd insist. But old Marsh George, who was the head engineer on the Hanford project, with baleful glare, with a roar that shook the air, cried, damn it, give it stuff to spare. The longhairs may have missed. And actually, it turned out, I won't go into all the details, but it turned out they needed that extra. If they hadn't put that in there, we would have no plutonium. So another very lucky thing for the Manhattan Project. Now, again, in a reactor, you start out with 238, you basically are going to generate some plutonium in the reactor, but you got a whole lot of neutrons, and what happens eventually is the plutonium undergoes fission in the reactor. You don't want that. What you want to do is push the fuel rods out of the reactor at the maximum amount of plutonium. Okay? That makes sense. So, you push the fuel rods out of the reactor. You have pure plutonium? No. This is what goes into the reactor, and this is what comes out of the reactor. 238, it's mostly 238 in, 238 out. You get a little bit of plutonium-239. Now, what do? The physicists that built the reactor, the engineers built it. They're really in deep doo-doo, right? Who do you call? A chemist, right? There's the chemistry. Don't worry about it. Basically, what you're trying to do is extract that little bit of plutonium out of all the other junk in the reactor. And it's got to be 1 part in 10 to the 7 parts purity. You cannot have any impurities in this plutonium because impurities will impede the function of the bomb. Okay? Now, you don't take this to the laboratory and do it on a laboratory bench. You do it inside one of these buildings. These were known as Queen Marys because they were as big as the Queen Mary. Nobody goes inside that building. This is all done by remote control. Okay? There were 5 of these processing plants. They took the material from the reactor and extracted plutonium. There's what it looks like inside. All the chemistry is being done underneath these guys. Notice that they're in protection suits. First use of television to monitor what's going on now industrial television. So a lot of technology, really amazing chemistry that's done with nobody down there. Now, Manhattan Project had spread all over the country. The primary facilities were Oak Ridge, and you can see the contractors. U-235 at Oak Ridge, Plutonium at Hanford, everything went to Los Alamos, all the material. Carloads of stuff would go into these plants, and suitcases of stuff would come out. People wondered, you know, you got these big plants and nothing's coming out? What's going on? Okay. Notice, too, that a lot of other organizations were involved in the Manhattan Project. Milwaukee, Detroit, St. Louis, just you name it. There was some probably, in your congressional district, there was probably somebody who was working on the Manhattan Project. Again, beginning of military-industrial complex. Now, everything goes to Los Alamos. How many of you have been to Los Alamos? It's a very kind of a magical place, right? It's built on the fingers of a volcano. The lands are on here, and you have big canyons in between the lands. It's up on top of a plateau on these lava flows. And what was done at Los Alamos was basically what came from Oak Ridge was uranium hexafluoride. The chemist and metallurgist at Los Alamos reduced this to metallic uranium, and that's what you put in a bomb. You don't put uranium hexafluoride in a bomb. You got to convert it back to uranium. What came from Hanford was plutonium nitrate, and again, it was reduced to metallic plutonium, and that's what goes in the bomb. Now the bombs. There's a picture, actual picture of Little Boy and Batman, and you can see that Batman was supposedly, I think, maybe named after Churchill. There was another plutonium bomb that the design didn't work out. It was called Thin Man, and I think that was Roosevelt. But Little Boy, I don't know where that came from. Maybe somebody knows. Now, requirements for Little Boy. Assemble a supercritical mass in a microsecond. Initiate a chain reaction, and you can do that. I'm not going to tell you how to do that. We don't need to detail. And keep the mass together for 1 microsecond in order to have 80 generations of neutrons to generate that tremendous energy that you're going to get out of all those uranium-235 atoms undergoing fission. Now, the Little Boy mechanism is really simple. It's nothing but an artillery barrel. This is basically an artillery barrel. What you do is you fire one piece of uranium-235 into another piece of uranium-235. Assemble that critical mass very quickly and initiate a chain reaction. And you got it. So that's a little point. The Navy people, actually a naval auxiliary officer named Frank Parsons was in charge of this triggering mechanism. Okay. Somebody was worried about what was going to, did they have the right kind of gun barrel? Is it machine right here? And one of the Army guys said, hell, the thing's going to blow up, quit worrying about it. Now, the other one, the plutonium triggering mechanism, is much more complicated because uranium emits very few neutrons per second. When you produce plutonium-239, you also get a little plutonium-240. And that's bad news because 240 emits lots of neutrons and just spinning off neutrons. Well, what happens when you try to bring those two pieces together? This plutonium-240 throwing out these neutrons, you get a premature detonation. In other words, a fizzle. So you cannot use the gun barrel design as a mechanism for plutonium-231 bomb. So, what did they do? What do you do when you get in trouble?
Call accountants.
The chemist was George Kistakowski. The mathematician was John von Neumann. And together, he worked on the theory of creating shock waves with conventional explosives. So what you do is you surround your plutonium with conventional explosives and you squeeze it together to make a critical mass. Okay? So this is called an implosion device. And it's a much trickier triggering mechanism than the gun barrel. Now, they didn't really need to test the gun barrel. They felt like it would probably work. Probability was pretty high it would work. The plutonium bomb, they felt like they needed to test it. They had enough material in July 1945 for 1 uranium bomb and 2 plutonium bombs. So in order to test the bomb, they put it on a tower in Alamos, New Mexico, and they had a successful test on July 16, 1945. And here you see two very happy people, General Rhodes and Robert Oppenheimer. Now, just to give you an idea of the command that the structure that created the bomb, and where General Marshall's role was. General Marshall was kind of in the middle of all this in a way. You have the top policy group, you have a military policy committee, which General Rhodes ran. You have an interim committee, which really decided on how and when the bomb was going to be used, which had both military and civilian people. And then everything below this, though, is run by General Rhodes. General Rhodes not only made the bomb, but Marshall said, well, we want to keep this in the family, so why don't you chair the committee, the target committee? You be in charge of dropping the bomb. So Rhodes assumes more and more responsibility. Rhodes' assistant was Colonel Nichols, and you have here Clinton engineering work with Oak Ridge, Hanford, and Los Alamos. And then you had a lot of other companies throughout the United States. Okay, recommendations from the interim committee. Jimmy Burns was President Roosevelt's representative on the interim committee. The interim committee was supposed to address how nuclear energy would be used during the war and also after the war. Mr. Burns sort of took charge of the committee. Marshall was there. He was a guest, but he participated a lot in the discussions of the interim committee. We talked about that last year. But basically, the interim committee said, we recommend the Secretary of War should be advised final selection of target was military decision. View of the committee was the bomb should be used against Japan as soon as possible on a war plant surrounded by workers' homes, and it was to be used without prior warning. Marshall had suggested that we might give a prior warning to the target areas. Burns overruled that. Now, the official orders to drop the bomb are here. They're signed by a VMI graduate, Thomas Handy. Handy was in the Pentagon. Marshall was at Potsdam. So he's the guy that really signed the orders to drop the bomb. Truman didn't sign any orders to drop any bomb. He didn't stop it. That was the main thing. He didn't get in the way. Anytime after August the 3rd, start dropping bombs and drop bombs until you know, and then we run out of bombs on the Japanese threat. Now, the mission to Hiroshima was flown from Tinian Island. It was a perfect mission. The attendance crew did a perfect mission, no hitches whatsoever. Everything went off the way it should have. The mission on August the 9th was far from perfect. They flew around, the clouds were covering the targets. They finally, they were not supposed to bomb without visual sighting. The clouds miraculously opened up over Nagasaki and they dropped the bomb. They missed the target. The target of Hiroshima, they hit exactly where they wanted. The plane had to go back to Okinawa because it was running low on fuel. They landed, and just as they got to the ramp, so to speak, it ran out of gas. So they were very lucky to get back to Okinawa. Now, not a very pleasant slide, but we're talking about weapons, so we have to talk about the effect. Little Boy was dropped on August 6, 1945. And you can see the stats here, but the stat is very interesting. It had 132 pounds of U-235. Only 2 pounds underwent fission. It's a very inefficient bomb. Today's bombs are much more efficient, trust me. All right. The height of the blast was 1,900 feet. People often ask me, well, how can you go into Hiroshima a day or two afterward and not be exposed to tremendous amounts of radiation? Well, if you dropped the bomb and dug a hole, you would radiate all the material. If you do an air burst, you don't radiate anything like as much material on the ground. Okay? And you can see the casualties there. Fat Man was dropped on Nagasaki. Again, it only had 12 pounds of plutonium as opposed to 132. Only 2 pounds underwent fission. And it was a little more powerful. But since they missed the target, it didn't cause as much destruction. Now, there's the New York Times when people first found out about this. There are the headlines. So you've got August 6th, and then you have August the 9th. So you have the first atomic bomb on August 6th, the Russian invasion of Manchuria on August the 8th, and the second bomb on August the 9th. Now, the folks at Oak Ridge and Hanford, they didn't have a clue. Most of them didn't have a clue of what they were doing. I mean, some of the physicists that give us probably had a good idea, but most people didn't know. So here's the headline in the Knoxville News Sentinel that the Oak Ridge people saw, and here's the headline in the Pasco Herald, which is right next to Hanford, which they saw. Now, how much did this cost, and how do you compare it? Well, the atomic bomb project in 1996 dollars, and I think you could probably multiply that by about maybe a third. It's $20 billion for 3 bombs. And you can see the comparison with other weapons here. So the average price of the bomb was about $7 billion in 1996 dollars. How many people worked on the Manhattan Project? Manhattan Project employed 625,000 people from the beginning to 1946. And you can see that the blue line, these were people involved in construction and design, and then the other people were involved in research. Marshall was the ultimate manager. He held the ultimate responsibility for both the money and the people. So he is certainly in the equation. So, here's what Truman said when he gave him the Distinguished Service Medal in the fall of 1945. He obtained funds from Congress. He obtained from Congress the stupendous funds that made possible the atomic bomb well know that failure would be his full responsibility. So that's what Truman thought of Marshall. And finally, Marshall recognized that the atomic bomb had changed warfare as we know it. And he basically said the implications of atomic explosion will spur men of judgment as they have never before been pressed to seek a method whereby the people of Earth can live in peace and justice. If man does not find a solution to world peace, it will be the most revolutionary reversal of his record we've ever known. Our diplomacy must be wise and it must be strong. So this is kind of what Marshall got out of all this. So there's the science, the technology of the atomic bomb. We basically won the race. We knew in 1944 that the Germans really had no atomic bomb project, but we kept plowing on with ours. And the race then became to build a bomb in order to get the war over as soon as we possibly could. And we can have lots of debates about whether the Russians or the bomb or whatever ended the war. But this presentation was basically to give you some idea of the Manhattan, the science, technology, and the scope of the Manhattan bomb, which Marshall had the overall responsibility for. Thank you.
Easily, where is Iran in this process of developing a bomb? How close are they to having a bomb?
I'm not sure. I mean, actually, obviously they're separating uranium, so they're going for a uranium bomb. Now, the triggering mechanism on their new uranium bombs is the same implosion mechanism. They don't use the gun barrel anymore. So, you know, it's not, I mean, they know how to put together something. So I would say, you know, if indeed they decided they wanted a bomb, they could probably have a bomb in 6 months to a year. I mean, it's not, everything is well known about how you assemble it. So it's not inconceivable that they can put one together. The other question is, once you have a bomb, you need a delivery system. I mean, you know, how are they doing with rockets and that sort of thing? So, but basically you need to monitor carefully the production of that U-235. And U-235 is used in nuclear reactors at a concentration of about, what now, 4 or 5%.
Yeah, something like that.
So they don't need to be taken at any greater than 4 or 5%. You know? And we can monitor that. That's part of the deal. Now, whether we can enforce it or not, I'm not a diplomat, I can't argue it, but it is enforceable. Okay? And if you want my opinion, I'd rather have a deal than no deal. Because no deal means they're going full fledged with no restrictions. Yeah.
How powerful are the bombs today in relationship to the bomb back then?
I wish I had brought the slides that I have. I have a slide that shows mushroom clouds. Hiroshima and Nagasaki are here. The hydrogen bombs are up here somewhere. And the intermediate bombs are, you know, Hiroshima and Nagasaki are like pea shooters.
Compared to what we have today.
Yeah. And if you look, it's interesting to me, one of our nuclear submarines, right, carries, I think they carry about 24 missiles. Each missile carries 4 warheads. So you got about, what, 100 nuclear warheads. Each one of them probably 100 times more powerful than Nagasaki. And we've got, at any one time, we probably have 6 or 8 of those guys out floating around.
So it doesn't really matter too much, you know, compare America's arsenal versus other countries' arsenals, because just one bomb, if they just have one, that's going to devastate
a given area.
A given area.
Yeah. Now, whether, they're, as I said before, the Hiroshima and Nagasaki bombs were pretty inefficient. We now have something on the forehead that is maybe something like, almost like this, and very small amounts of material. But the triggering mechanisms and things, they've improved those immeasurably. Yes?
All right. When you talked about Hanford, you talked about the Queen Elizabeth or Queen Mary's with no one inside.
Yeah.
Could you comment on the reason for that, the toxicity of plutonium?
Yeah, the chemical toxicity or plutonium, it's interesting element. It's named after Pluto, the planet Pluto, but Pluto is also the god of the underworld. And so it's a real apt name for an element. Chemically, it's very toxic. And radioactively, it is an alpha emitter, which means if you ingest it or inhale it, you're going to have alpha radiation in your body, so you can't get around it. Is that?
Yeah, that's
more or less. It's bad stuff. The other thing at Hanford, when you extract plutonium, when you extract a little bit of plutonium, you create a tremendous amount of waste. And we are spending billions, literally billions of dollars cleaning up that waste. Because we didn't worry too much about it while we were trying to beat the Japanese and win the Cold War. And so we took better measures than the Russians did with their waste disposal. But still, we put it all in big tanks out at Hanford, and those tanks now are corroding and leaking potentially into the Columbia River. But they're working to stop it, but it's a mess. Yes, sir.
When dams and bridges are built, people working on them die. What kind of rate of mortality do we have of these 625,000 people due to industrial accidents during that period of time?
I really don't know. Workers were exposed in various places. I watched a documentary not too long ago about the workers at St. Louis, Missouri, or Kansas, St. Louis, I guess. And they were making plutonium for their trigger mechanism. And they were exposed to really not. Part of it was, we may not have known that much about it, but the other part was, we needed that material. And we basically were willing to sacrifice some people or expose people to radiation. So, yes, workers were exposed. And the terrible thing was that prisoners were injected with these compounds, some of these compounds, by the Army, I guess. So, we don't have a really great track record of handling this stuff.
What was the neutron bomb abandoned?
That was one that was going to release a whole lot of neutrons and not have anything like the explosives to flash and a burn. It was basically going to release neutrons, and neutrons are very destructive to your body tissue and things, but they don't seem to bother buildings all that much. So if you're inside a tank or something and you get a flash of neutrons, you're going to kill the people in the tank, but you basically don't worry. So the explosion part was sort of minimized, the neutron emission was maximized. That's a simple answer.
Why was it abandoned? It seems like a much more efficient weapon.
I don't know the workings of the Department of Energy. I don't know. Jimmy Carter, I think, was one of the proponents of it. Well, that may be why it was abandoned.
Were there any targets in Europe that were considered? I know that the European war was over before they came online, but had they considered any European targets?
That brings up an interesting incident that's in the book, actually. After the Hiroshima bomb, Curtis LeMay, who was not a very withdrawing figure, if you remember, Curtis LeMay came out and said, you know, if we had the bomb in Europe, if we waited just a little bit and had the bomb in Europe, we wouldn't have had D-Day. Oh my God. I've got the memo that Marshall sent to the play is in the book. And he was not happy with that. I don't know, I don't think they were followed up. The target committee for Japan was not convened until April 1945, so I don't think they really felt like it was going to be used on Germany. Yeah.
You mentioned how much of the fissionable material was actually exploded, or whatever you call it, in the two bombs in Japan. Is that a calculation somehow that they arrived at that, I suppose?
Yeah.
Or,
Well,
working
they have a
backwards?
way of looking at shadows and various data that they went into Hiroshima and Nagasaki and got. So I'm not sure exactly how that was done, but yeah.
Was that about what they expected? Or did they have any idea of how much of it would
Well,
actually go off?
after the Trinity test, they had a pretty good idea about the plutonium bomb. And there was a pool of scientists, and they were all taking bets on how this Trinity test was done. And some of them were going at, like, maybe a kiloton, and you go up to maybe 20 kilotons. Enrico Fermi said he bet it would incinerate the universe. So they were all over the map with their bets. But there was a lot of uncertainty about the bomb. And Marshall had to, the book kind of points this out, Marshall had to deal with this uncertainty. He had this weapon, but he really didn't know whether it was going to work. He was looking at an invasion that he certainly didn't want to pull off. So anyway.
No.
Did the test bomb that they set off have the same relative characteristics of the explosion? They had an inkling that it was not going to be.
Yeah, it was the same one they dropped on Nagasaki.
We're going to hold off on any more questions. If you have more questions for Frank, he'll be available upstairs in our reception. Just wanted to thank you, Frank, one more time for your very in-depth look at the science and the history behind the development of the atomic bomb. For those of you who are here this evening, if you want to come back and join us at the Marshall Foundation on Saturday at 1 p.m., we are going to have a NASA astronaut here, Patrick Forrester, to speak about NASA's Marshall Space Flight Center, aptly named after George C. Marshall. And he'll also be just talking about his career as an astronaut as well. Thank you again. We will adjourn to a reception upstairs. If you have not had a chance to view our exhibition outside for the Legacy series, From Man to Machine, please take a moment to go look at that. Otherwise, I look forward to seeing you guys upstairs. Thank you again for coming out this evening.